Okay. Okay. This is my, let's write it as A. This is my B. A, B, C, D. Correct? Good morning. This is A, 36.
Problems.
Yeah.
They never end.
Yes. Yes, that's and that's a problem. So 0.00.
Problem hocam yani.
Yes.
Very very huge yani.
Yeah, I know.
What can I say yani?
Yeah, I hear you. 0.002 meters square. Right. And this one is A3, A1. This is 2 meter, 1 meter, 1.5 meter. So 2 meter. I hope it is visible. 1 meter. This one is 1.5 meter. Correct? And this is 1 meter. How many agree? And this one is 2 meter. No, we haven't. We haven't. The diagrams just take so much time, on whiteboard, on Zoom. So that's why because if I start making this at 10:40, I will do it in a very, hurriedly, and then the diagrams will not be good. So I start 5 minutes early just to buy some time. Okay. Okay. I have a 2 meter here, right? Okay. And I think it's a straightforward problem. You can put some color just to be clear that we are talking about a solid object. No, we will start at 10:40. It's just drawing takes too much time of me. I'm drawing it. I will say everything at 10:40. So it's the same object. A36 steel. Sure. So this problem is definitely going to be done by all of you. Then I will make one more problem, the statically indeterminate. You will use the imagination. Okay, elastic modulus, I did not give you. That is 200 into 10 power 9 pascals. And then boom. Do we have everything? We have. So first, this problem will be done by all of you. Then we will move to next problem of the day. We have few more strain problems, but I will keep on throwing them in. I really want this week you should have idea about statically indeterminate problems as well. So that will be our next example. But this one is easy, by the way. We have done something similar. Yeah, okay, we will wait for every student to arrive and then we will start. Ehsan, can you hear us? Ehsan?
Yes, Jam, I can hear you.
Okay. Our lighting is good, right? Okay, everyone. 10:38. 10:39. Okay, we have 10:39. We have 60 seconds. Okay, great. I think you can start. No, I will wait for the clock. Good morning. Good to see you. 10:39, 10:39. Oh, hang on. I did not. Yes, sorry. I did not tell you the important part. You have to find the total change in length of the whole object. Sorry, I forgot. So give me the change in length for the complete structure. 10:48 is okay. We can start. So this is your problem. We have this object now. What you have to always understand is that there are three ways that you can see a discontinuity, if I am allowed to use that word. One is change in area. One is a force that shows up somewhere, point of application of, application of force. So change of area, change of force, change of material. You don't have a change of material here, right? The whole thing is a A36 steel, but you have a change in area, right? And that change in area is at B and C. You also have forces at B and C. So B and C are definitely the places that I have to be very careful about. In order to tackle this problem, you will divide it into pieces and chunks. So the places that you are seeing change is B, right? So you will make a cut here, then you will make a cut here, then you will make a cut here. When you make a first cut, you will throw this chunk away. When you make your second cut, you will throw this chunk away. Then you make your last cut. Oh, really? Do I need? Okay, I will throw this chunk away. So why don't you give it a shot, everyone? I will do it along with you. So I have this feeling that this total is equal to delta AB plus delta BC plus delta CA. And my whole problem is divided into finding delta AB, which is equal to PAB, LAB, EAB, AAB. Okay, I'm definitely sparing some time. You can write the expressions for them, for these as well, for now. Okay, now the next, okay, in fact, nothing harm in it. Let's do it together. Delta, I hope I don't lose internet because I have written so much here. Okay, then P, BC, L, BC over E, BC. Now it's just EBC and EAB are the same. So I'm not even sure why are we even bothering to write AB and BC. A, BC and delta CD is equal to P, CD, L, CD. Of course, we are in the elastic zone. E, CD, A, CD, correct? Okay. So the last, hi, hello. Last piece of the chunk is, in fact, the mistake actually happens here. You have to use your statics actually, and statics, you have to find PAB. I will use my statics principles and I will find and I will make a nice and beautiful rod like this. And I will make a cut. Right? Wrong. This is my 100 kilonewton. I have made a cut. I made a cut and I am putting a nice and beautiful arrow like this in this direction. So honestly, as we proceed with a lot of practice, you can have your own, approach. I usually, when I'm not sure, I usually draw outward arrows, but anyways. So I think it's pretty clear that if 100 is there, then the reaction will be here. So it's not even a point of contention. I will put a PAB here. Then I will make a rectangle here, free body diagram, as we call it. This time around, my rectangle will be big, like somewhere here. So I have technically made a cut. Are you getting my point? So now I will make a cut. This time around, I have 100 here. Then I have somewhere here. Next force, that is 250. Did I make an arrow? Yeah, 250 in this direction. Boom. 250 here. Correct? And then the last but not least, I will make another cut. Boom, somewhere here. Right? Let us see. Yeah, right. Okay, let us make a little bigger. I don't want anyone to get confused. So this is my 100. This is my, what was that, 250? And this is my 300, somewhere here, right? 300. And this is, okay, did I miss? Yeah, I think I did not mention here. So 100 here, 250 towards right. So I think I will have a reaction like this, right? Am I correct? Minus 150. Yes, 150 here. So let us call this as my, okay. Okay, I think I need to explain something. Yeah, because now it's going to get a little confusing. Or probably not. Okay, so let me draw. This is my P, BC. Okay, And this one, 100 in this, 250 here, 300 here. Do the maths. It will be 150 here, 300 here. Will I have something towards the right? Right. I think so. So reaction, yeah. So 100 here, 250 here, 150 here, 300 here. So yeah. So this one will I will call it as my AB, PC, no, CD. So CD. This is my PCD. I have made a cut. Okay. So now let's do it. So PAB equal to 100. Boom. PBC comes out to be negative PBC, negative 100 plus 250, and I get equal to 0 because of Newton's law. So I get PBC as 150. In which direction? In this direction. I get PAB in which direction? In this direction. And I get minus 100. Let me do it here. Minus 100 kilonewton plus 250 kilonewton minus 300 kilonewton plus PCD equal to 0. So I get, what you can use a calculator, minus 100 plus 250, that is minus 150. PCD will be 150. Okay, 150 in this direction. Now for students who actually put the arrow of this outward, because trust me, I even don't like this one. I usually put arrow always outward. Then if you put an arrow outward, your PBC will come out to be negative, and again it will indicate that the force is towards left. So anyways, now the last piece of the puzzle is doing the number crunching. I'm not doing it, you do it. So all I'm saying is, why don't you do number crunching for me? Is it even visible, the green? Probably not the best choice of color. So PAB, LAB over EAB, AB, give me the answer for that. Delta BC, give me an answer for that. And delta CD, give me an answer for the, now you have to be careful here. Hang on. You have to tell me which portion is in extension, which portion is in compression, which portion is in extension or compression, because all three of them, one or two of them might be in compression as well. And that's the only tricky part of the problem. So I just said you have to tell me which part of the structure is in compression, which part of the structure is in tension. And you also have to, of course, give me delta AB, delta BC, and delta CA. Is it clear to Ehsan?
Yeah, yeah.
And what about, we have a lot of students today. Ehsan, Hafad, Muhammad Khatabi, Muhammad Marij. We also have Sadiq Atta with us. Okay, just tell me if the tabs are. Okay, so yeah, so yes.
Question. When PCD towards left, if we get the part, small portion in CD, we are getting the bigger part, and there is also small portion we are not.
You mean
including.
if I approach the problem from right hand side?
Yeah, we are, when we look at the small part, the PCD will be in left side, right? It will be because there is a tension in CD.
So you draw it here. Yeah, CD.
Yeah, the big portion is like this, and there is a small portion in CD. The force is.
Yes, CD is in tension. CD is in tension. You're right. If I look from right hand side, if I look from right hand side, I will draw a cut, and I will see that by making a cut,
the PCD will be like.
Exactly. If I make a cut from here, right, through CD, I will see 150 is here. I will have to put a reaction of 150 there. So it's pull in. So the CD appears to be in intention, you are right. Now look at AB. If I make a cut between A and B and I throw the right chunk away, 100 towards left and 100 here, I will see that this is also in tension. AB also looks to be in tension. But look at BC. If you look at BC, everyone, this is my BC, right? So you see that
This one, AC, I guess.
BC, yeah, BC I'm talking about. BC looks to me, this portion looks to me in compression, because if you see here, 150 PBC is 150 is acting like this. And if you sum both of them, 250 minus 100, this chunk is like this. So this rod is in compression. So my BC looks to me in compression. Right? Look, 250 minus 100, right? So you have a resultant in this direction. And in order for the statics, you can see PBC I came up with towards left. So this bar looks to me in compression. So I will explain it further, but one of you needs to tell me delta AB, by the way. Delta AB is dimensionless and it came out to be 0.001, right? Yeah. Something like this. Delta BC came out to be minus 375 into 10 power minus 6 meter, and delta CD comes out to be, anyone? 1.125 into 10 power minus 3 meter. Okay, and for those of the students who are saying, why on earth did you put a negative? Look again, if it's in compression, and just to be clear, as a student, I always used to actually draw outward arrow. The PBC will come out to be negative. It will, again, I will put the PBC here. Where is the formula? Here, and the answer will come out to be negative, or even with observation, you can see that this is inward arrow and the whole structure is in compression. So why don't you give me the delta total? Quickly. Oh, okay, not quickly. You can use a calculator and take your time actually. It is correct. This is clear, right? Do you have any questions? Are you positive? I can repeat this question again. Yeah.
Why didn't we write delta CD in delta?
Why didn't we write delta?
Why we wrote delta CA?
Oh, that is a typo. That is a typo. Sorry. That is a sorry for that. Delta. He's right. Delta AB, BC, AB. Yeah, that is just a typo. Thanks. Good. Yes. Okay, everyone. So somebody said 1.75 millimeter. Where is that? 1.75 millimeter. So the overall structure is in tension. The length is overall increasing. Delta total comes out to be a positive number. If it came out to be negative, then that means the overall length decreases. So life seems pretty good right now. What I will do is I will break the sequence a little bit. I will immediately tackle another problem, but you will see what do I mean by the next problem will be different. Okay, and just to be clear, you can just write equal to summation delta I here. Okay, I think you understand from maths, delta 1 plus delta 2 plus delta 3. I'm just adding all the little components. 7, 6, 5, 4, 3, 2, 1. Let's do it. I will make a little more complicated problem, and you will see. In fact, I will make your life a little easy here. Let me share the screen. Let me open the textbook so you see a nice and beautiful textbook drawing instead of no need to record. Pause. Yes. I'm not repeating the last sentences, but I will cover it like this, that this problem is different than the previous problems, because if I ask you what is the reaction of RA and RB, you can say that RA and RB, the sum of them is equal to how much? 900, right? But that's the end of the story, right? RA plus RB is 900, game over. But if I ask you what is RA and what is RB, can you tell me? Not exactly. Just by looking through statics principles, you will just stop. This is known as a statically indeterminate structure. INDETERMINATE. Statically indeterminate structure, where statics holds his or her hands in the air and says, I cannot help you anymore. That's statically indeterminate structure. So you take a picture, make a drawing, we will do it. So let me tell you the question. The question is, give me the reaction at A and B. That's the first part of the question. The second part you can say is, give me how much, let's say, the portion AD has deflection, how much DC has deflection, how much CK has deflection, how much KB has deflection. Did you understand the question? Can you tell me how much is the total deflection of the complete structure? Everyone, can you tell me how much is the total deflection of this structure?
When you're saying deflection.
Total deflection means total change in length of the structure.
Oh.
Just by looking, you cannot? Okay, we will talk about it. For now, you make a picture and then we will talk. Total deflection will be?
Negative.
No. Total deflection. How much this complete structure can deflect? It is constrained from there, it is constrained from here.
So
0. The complete deflection of the structure is 0. It's constrained from both ends. There is a pin joint on top, but that pin joint will come into the picture if you had, let's say, a transverse load anyways. But in this, you in any case have an axial loading, and I'm focused on something else. So the answer is, I think I made my point. I have to go to the whiteboard. So let me draw a picture myself now. So let us do this. You know what? Let me do something. I really want to make my own life easy as well. Let me use my own imagination. So I will do like this. Then I will do this. Then I will just open the paint. And then I can combine the files and we'll post it. So don't worry. Okay, let's share the screen for our students. Okay, I will save it later. Okay, share the screen, admit. Let's do it together. So let's do it together. Okay, number one is I am asking you to give me deflection. Now, what did I tell you the rule? There are 3 things that can cause discontinuity: change of material, change of area, change of force. Got it? Now, do I have change of material? I don't think so. I think it's the same material. Do I have change in area? Absolutely. I have a change in area at C. Do I have some forces that are acting? Absolutely. At D and K. That's why my points of interest become A and then D and then C and then K and then B. So my question is, give me delta, hang on, give me delta, let's say 1. Give me delta 2. For students who are wondering what on earth is 1, I mean AD. I think I mean DC. Then delta 3. Give me delta 4. 3, I think I mean CK. You can either use 3 or CK, whatever. And this one means, I think, KB.
Hocam, there's a pin joint at A, right?
There's a pin joint at it. But then at the end of the day, even the pin joint, I'm putting an axial load. It is taking the load, right? Pin joint does not support moment, but pin joint is taking the load.
Yeah.
You are definitely doing it. Do you have any question? Anyone? Everything is fine. So do it quickly. At least start the problem. So this is a statically indeterminate structure.
Will you give an elasticity?
Yes, sorry. I think you're right. Thanks for pointing out, by the way. I think I need to give you. No, elastic modulus is not given. Don't worry, you will not use it.
We just want to drag towards the A and B, right?
No. Yes. So you want to find that, but you cannot just find it right now. So right now, what I'm asking you is, so let me tell you what I want from you. Okay. Make a cut between A and D and throw the bottom chunk away and tell me what is the reaction that is acting here. Here. So you will say that, okay, I will start the problem. So let me start the problem for you because this is a very new problem for everyone. So this is my first chunk. This is my RA. So first of all, in the free body diagram, let me draw a free body diagram for you first. This is my original structure, right? And then I have something like this. 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 Let me do it very quickly. Okay. And then I have something like this. Okay. This diagram just became horrible. So let me do it like this. Okay. So my first step is that I will put, let's say, RA like this, because my intuitive feel is if both the loads are acting downward, then RA might be upward. And second, I will put RB here, right? Then I will start making some nice and beautiful cuts. This is my D and this is my K. Please make a cut here. Let me make a purple line here. So now you tell me, when I make a cut, this is my RA, correct? So this is my, let's call it as our, hang on, let's call it as our 1. This one will be my AD or whatever, PAD. How many are comfortable with PAD or how many are comfortable with 1? I think let's call it as 1. I don't know. I like it better. P1 or PAD, whatever. Good. So then I will make my second. Oh, come on. Where is the purple one? Okay, this one. The second cut I will make here. Correct? And I will say this is my RA. Cannot play with it. This is my PDC. or P2, whatever. I don't want you to get confused, so I will start writing AD as well, so everyone is on the same page. Or this one is my DC. Got it? Okay, then last cut is, okay, let me do a save. Life will not be good if this gets vanished. Where is it? Downloads untitled. Okay. This one will be, okay, why don't you tell me what should I do now? Till where? Quickly. Till where should I go? Huh? Till here? I think I should stop till here, right? Because the area is changing, right? So I will put my next cut here. This is my, again, RA. Last part of the problem, definitely you are doing it. RA. And this is my, no, this is still here, right? So this portion is my, yes. So I will write it as my P, CK, or I think I was naming it as 3. P3 or PCK, whatever you are comfortable. And the last one is, okay, I have crossed K, right? Good, I have crossed K. Now I will make my last chunk as nice and beautiful RA. And this one will be P4, or let's call it as, what is that? KB, right? KB, PKB, P4. So now I'm done. Now you are completely confused till now what exactly is happening, right? Look, I am asking you to give me the deflection in the first chunk, that is between A and D. Then I'm asking you to give me the deflection in the next chunk, that is DC. Then I'm asking you to give me the deflection in the next chunk, that is CK. Then I'm asking you to give me the deflection in the next chunk, that is KB. That's what I'm asking you. In order for me to know the deflections, I know the formulas. And the what is the formula? Anyone who remembers that? P, L, so again 1 or AD, whatever. P, AD, let's call it as 1. P, L over EA, right? Yeah, I think that's the right answer. It rings bells. Yeah, got it. You got it. Yes. Done. You already did it. Good. That was very fast, by the way, but good. So delta A1 is this one. Then the next one is delta 2, or we all said, let's call it as DC, whatever you are comfortable with. P DC, L DC over E DC, A DC. And the last one is delta 3 CK equal to P CK. If someone doesn't want to use the CK and wants to use a 3, I have no objections. CK, E3 or CK, A3 or CK, whatever. And similarly, delta 4, what was that? KB equal to P KB, L KB, 4 KB over E 4 or KB, whatever, A4 or KB, whatever. So honestly, the problem has at this point ended. Actually, all you have to do is just do number crunching. 6, 5, 4, 3, 2, 1. So I have to scroll because I don't have space. Just bear with me, please. So now let's add it together. I know that delta total equal to delta 1. Come on, where is it? Delta 1 plus delta 2 plus delta 3 plus delta 4 equal to 0. And then you will play this little game. You will say it is P1L. Okay, I have already forgotten what was that. AD. P1 AD L AD over E AD A AD plus P2L. What was that? I actually don't remember. Okay, DC. Thank you. DC. DC over E, DC, A, DC, plus we have P3, CK, CK over E, CK, A, CK, plus P4, KB, E, KB, A, KB equal to 0. Now I will not wait, by the way. What was P1? Where is P1? Okay, hang on. P1 is, so I will actually do all the steps because this is the first time you are doing it. So I will do all the steps. Summation Fy equal to 0. So I will have positive RA. Let me use a very different color. Positive RA minus P1 equal to 0 and RA equal to P1. Boom! RA is P1. Here it goes. Oh, come on. RA. Yeah, here it is. RA. Let's play the same game one more time. For this chunk, I have positive RA. I think I am making a mistake, by the way, in all these drawings. If this is RA, then why did I miss this? Sorry. Yes, I made a mistake. I have to correct it. So there is a load acting 300 kilonewton here. So there is a 300 kilonewton load. Sorry for that. So here I have 300 kilonewton of load, which I forgot. And here I have a 300 kilonewton of load, which is acting downward direction. Sorry. Load at K is 600. Yes. Okay, thank you. So load at K, again, I am forgetting. So it is, thank you. It is 600. Boom. That was the only mistake I was making, and you can actually make a line if you want. So you are sure. Abdullah has joined. Okay. So now that I have corrected my mistake, I will go back here, RA minus 300. Minus 300 kilonewton. That is minus, this is minus, right? Are you following me, everyone? Minus P2 equal to 0. And we have P2 comes out to be RA minus 300 kilonewton. So what I will do is I will put a box around it, and I will put a box around it. And wherever I see a P2 now, I will put RA minus 300. Okay. Oh, come on. But now from here onward, you do it yourself. So wherever I see P2, I put RA minus 300. Here I see P2, I put RA minus 300. Why don't you tell me what would I put in P3 and P4? I think you are already P3 and P4. Why don't you tell me to do this complicated? Okay, let me show the drawing. Okay, why don't you tell me? Make a cut here.
50 equals P2.
Oh yeah, that's the same thing. Yeah, thank you. So it's thanks for mentioning this. It's the same thing. Where is the pen? Yeah, she is right actually. She's right that it's the same thing. No, let me do it for you. When you use this one, it's RA minus 300. Oh wow! So it is plus RA minus 300 minus P3 equal to 0. You can mute the mic, please. You can always unmute the mic whenever you have question, but if you have joined the class, just if you can do it, I would really appreciate. Thank you. So RA minus 300 minus P3 equal to 0, and we have we have P3 equal to RA minus 300. Yeah, you're right. So wherever I see P3, I put a, oh, come on, RA minus 300. P4, you are definitely doing it. Quickly. Everyone is doing it, so I will just finish the question then. So we have, let's do it together. RA minus 300 minus 600 minus P4 equal to 0. And you said RA minus 900, right? Equal to P4. So wherever I see P4, I will put RA minus 900. You are definitely solving it.
Come on, solve it.
Why we set the delta total equals to 0?
Oh, of course, because look, this is the crux of the problem, the backbone of the whole problem. That if you have a load here and you have a load here, at the end of the day, this object is constrained from top and bottom. So for this structure, as long as you have a rigid support here, and as long as you have a rigid support here, then there is absolutely no way that the total deflection of this total deflection will be changing. Total deflection will remain 0. Of course, if you have top support itself is not rigid, that's a different story.
So because we are splitting the part with two
Rigid supports. They are completely rigid. Okay, everyone. What about our online students? What about Abdullah, Ehsan, Izan, Hafad, Muhammad Khatabi, Sadiq, Aisha, Muhammad, Marriage?
Can you scroll down?
Yes, I will. Like here? Okay, perfect. Okay, everyone. And one last equation that I need is, what is the last equation? The last equation is, which I should have written before, RA plus RB minus 300 minus 600 kilonewton equal to 0. I will call this as my equation 1, and I will call this big chunk as my equation 2. Two equations, two unknowns. Life can't be more beautiful than this, right? Done. And just a quick remark that if the whole structure is made up of the same material, then EAD equal to EDC equal to ECK equal to EKB. So everything will go to the right hand side and will multiply with a 0. And LAD, oh really? I think L are also equal, no, in this problem. LAD cancels with LDC, will also go to the right hand side. That's an easy problem, by the way. So technically it will be the areas that will be the deciding factor, and two equations, two unknowns. So you will actually get a beautiful RA from here, and that beautiful RA I will be putting here. That will give me RB. Just give me the values of RA and RB. We are not going anywhere until you give me the RA and RB. The problem doesn't make sense, right? Total deflection is 0. The individual chunks had forces P1, P2, P3, P4. I started using statics, kept on cutting, and started writing those P1, P2, P3, P4 in the form of RA. Which one? RA. RA is the reaction. So if you make a free to this point, the hinge. So for example, if you make a free body diagram, in free body diagram, you will remove this exactly where my thumb is, and you will remove this portion. So you will have to and then you will have to put arrow here and in upward direction, and you will put another arrow in the upward direction for RB. So if you make a mistake, not mistake, if you assume your RB to be downward, I'm not sure. I think the answer will be wrong. So you have to make a good intuitive guess in the beginning that your RA and RB should be in the upward direction. No? Yeah, because it just does not make any sense that RB would be in the downward direction. Okay, what about our online students? Have they solved it? Okay, everyone. Well, that was a good paint file. I have RA as he already told us, 323 kilonewtons, and RB is 577 kilonewtons. The values that I get. 323 kilonewtons for RA, 323, and my RB is 577 kilonewtons. Should I even remove them? E's. I think I have already made my point clear that E's are equal because material is same. I have already told you that even the lengths are same. So I don't need to. And then I said that L will go to the right hand side, cancel. E. So you will have RA in the form of these areas, whatever. Take the value of RA, beautiful value, and put it in the first equation and get RB. Okay, life is good. I will wait for 2 minutes more. Why don't you tell me the values? Yeah.
So,
Yeah, I will. In fact,
because.
yeah, that's fine.
Yeah.
Okay. Okay. Okay, 6, 5, 4, 3, 2, 1. On that note, I'm saving it. And should I proceed or? Should I? Everyone is done with this? Okay, so we will proceed. And okay, everyone, let's talk about something more. So just to be clear, this is what I covered. Statically indeterminate structure. Indeterminate structure. I just told you that when our statics principles are not sufficient to complete the story for me, sufficient to give me all the forces, then we utilize our strength of materials principles and try to find the unknown forces. Okay, I think this would have been just a mere English sentence, but we already solved the problem. So now you get the point that RA and RB could only be found when you use 206. Yes. I can go back. Yes.
The road is not restricted by two rigid
Oh,
objects.
yeah.
The question will give the total strength, right? Or any kind of information to
Okay.
solve the
Got it.
question.
Got it. I will just quickly make this. I want to answer your question, so I will do this. Look, your question is, what if the problem is like this? This is actually your question. Your question is, what if I have a force acting like this of 400 kilonewtons, and I have a force acting like this of 600 kilonewtons, and this is my A, this is my B, this is my C. So your question is,
We can find.
so here you can directly find the RA. You don't even need that because the total deflection is not zero here. Of course not. Okay. So, okay, everyone, let's talk about a new concept. I still will keep on coming back over the strain problems. So let us talk about an entirely new concept. Please bear with me. So that concept is Poisson's ratio. So let's go. Just to be clear, the problem that you just did. So what I can do is I can probably share with you our midterm 1 exam from fall 2021 as well. In our midterm 1, that is pretty much the problem I gave to the whole class. So we had a horizontal structure. It was constrained from both ends. 3 or 4 or 2, whatever forces were acting, I asked them, give me the reactions, etc. So this problem looks easy, but in an exam setting, you should know. Okay, so I have this structure. I'm talking about Poisson's ratio. The structure is like this. And this structure is like this. Then I have in this structure, let's say I am putting a load in this direction. Nice and beautiful. What happens is that the object becomes something like this. And I think you will understand what I mean by that. The width will decrease, right? When it stretches. Everyone gets the point. And the object now takes this shape. I'm just about to make a horrible 3D drawing. I'm not even sure it makes even sense. Let me try my best to look at my notes. 3D drawings are not easy. So it becomes something like this. Yeah, so yeah.
The inner surface area increases, but the lateral areas are decreased.
Yeah, so it decreases like this and decreases like this. It just decreases the area. That's what I'm trying my best to do. But I think now everyone also understands that I am putting my best efforts into this 3D drawing. I will not give up. Yeah, this is just. In my previous semester, at one point, I was coming 30 minutes before the class, 60 minutes, and I was just making these drawings. Okay, done. So it becomes like this, and you can. Okay. It doesn't seem to end, by the way. So again, like this. Okay, I think you get my point. So now the load is acting like this. Beautiful. And the load is acting like this. P prime is equal to P, the reaction. This is my original shape. Right? So when I put a stress like this, shrinks right from here and from here, laterally. So this is my loaded shape. I call this as my loaded shape. The original structure has deformed like this. Okay. And let me talk about very quickly the strains. What are the strains? One is epsilon x. But before I do that, I will make nice and beautiful coordinate system. This is my y. This chunk is my, what is that? Z, right? Z, y. So x, y will give me a z outward, curl of the fingers of the right hand. So my x definitely. Oh, come on. I think okay, that's fine. I think somewhere here like this. This is my x. Okay. This is my x. Okay, and this is my y. This is my y, and this is my z. This is my x, y, and z. Done. Let's save it if internet goes. Okay. Okay, so the question says what are the strains? My first strain is epsilon x equal to change in length in the x direction divided by the original length, which is in the x direction, whatever the length is. Then my transverse strain is epsilon y equal to change in length in the y direction. You can see that it has definitely.
It have to be minus.
Absolutely right, because it shrinks. Very nice. Thank you. Change in length over original length. So yeah, this chunk will be in the negative value somewhat. Yeah, you're right. 100%. I agree with you. Yes.
And also, this delta y includes both side shrink, right?
No, this is symmetric. So it's the no. No.
It shrinks like this and shrink like this.
Oh, you
This
mean?
part and this part
Huh.
we include in delta y, right?
Absolutely. Of course. Of course. The whole length, then chunk from here and chunk from here. Oh yeah, of course. So epsilon z equal to change in length in the z direction over LZ. Okay, and please remember that epsilon y and epsilon z will be equal if the object is what is known as isotropic. So wood, for example, has its own fibers. So, you know, it behaves differently in different directions. But steel, for example, mostly what we use, we have isotropic. So if, for example, this was a steel rod, and if I am trying to pull it, if it has to have epsilon y and epsilon z, it will be equal because this structure is isotropic. Now, what happens is that we have something known as Poisson ratio, which is our today's topic. Poisson's ratio with a double S, by the way. Sorry. Poisson's ratio? Yeah, it is unitless. So it is equal to, by definition, epsilon y over epsilon x, and you can call it as epsilon z over epsilon x as well. And typically for materials, we have Poisson's ratio less than 0.5 typically. And we can do actually a quick problem as well for Poisson's ratio. But if I were you, I will try to cram this. Again, I just did not do a very good job of drawing, but it is clear that I'm trying to tell you that this fellow shrinks like this and shrinks like that. Okay. So you will do a problem, and this time definitely you are doing it. 7, 6, 5, 4, 3, 2, 1. This is the problem. Should I go back?
No, could we give a short
We have a break, 5 minutes. We are meeting at 11:43.
Yaz saati olması geliyor ya.
Adamlar bekliyormuş. Her şey alsın. Çoğu koca versin. Adamlar bekliyormuş.
So just give me an answer quickly. We were supposed to start, right? Okay, good. So why don't you just give me the answer for this quickly? Why don't you give me the answer for this? You can also give me an answer for this one. If you remember, we already did this problem, I think, in the last class. So I am putting a load of 12 kilonewton. Did I even make the axis, by the way? So yeah, the axis is the same. So it's 12 kilonewton outward, okay? Like this, the load. Probably I should have been a little more clear. 12 kilonewton like this. Outward, okay? The dia is 16 millimeter. The dia is 16 millimeter. Let me make the axis for you. If it is of any confusion to anyone, this is my nice and beautiful x-axis. This is my y, and this is my z. The yellow line means that the solid shaft has decreased in dia. So please remember, this is a solid shaft. I gave you an outer dia, I mean just dia, of course. There is no inner dia for this one. A solid shaft, or I mean solid cylinder. The yellow line means, oh, did I? Oh, sorry. I think I give you. Sorry, I did not give you the delta R. Yeah, that's why I thought that. So yeah, it's my mistake. So no, I did give you. Yes, I gave you delta R, and I gave you delta X, and I have given you 16 millimeter dia. Everything is given. Straightforward, right? So that will be 300 into 10 power minus 6 divided by 500 into 10 power minus 3. That gives me my this epsilon x. This and this are the same thing, right? The change in length in the radial is the same as the change in length in the y or the z. That is minus 2.4 microns. I put it here. Where? Oh, here. I mean, you have to find it. I'm sorry. So our online student can also tell me the answer quickly.
0.3
No. So it's somewhere less than 0.5 and greater than 0. So you have to find the strain. Change in length by original length. Did you divide? Okay. So it will be change in length over original length. Change in length is 300. Did I think I might have given you wrong values then if everyone's answer is coming out tomorrow. Oh, okay, give me 1 second. 300 into 10 power minus 6. Original length is 500.
Hocam, you don't need the original length because original length is the same for both of the dimensions.
No. 510 power minus 3. Original length will be the different for both of them because one is 16 millimeter. You get it? Okay, so this one will be what is the change in length? Minus 2.4 micron divided by original length is 16 millimeter. You are right. I'm wrong. Yes. So it will be 8. Yes, you are right. Or you can multiply the numerator by 2. You are right, actually. So yes, thank you. Good. Yes, I think you are right. 8 into 10 power minus 3. Great. Oh, I have a different answer than that, by the way.
Hocam,
Yes.
drawing this.
I'm coming to.
No, I got negative.
Yeah, I'm coming to.
0.5.
Okay. Everyone, I think I have to give you the answer. This is a little bizarre. I have to double check from my notes because is it the change in the radius or change in the diameter? Just let me double check. Please give me 1 second because yes, you can ask me right now.
Delta. We're talking about this
Together or not?
together.
Yeah, that's what I'm about to look into. Delta R, I have to look at my notes. So
it will be delta D, right?
yeah, I have to look into it. Yeah, thanks for pointing out. That's just a little
Answer 0.25.
answer is 0.25.
So it's the diameter not like this.
The change in
Diameter.
yeah, so it's a okay. I will look into it.
How? When I use it.
Okay. Give me just 1 minute. That's yeah, okay. Hang on. Total change in the radial direction. So I even don't need to look into my notes actually. So you see this is the total change. There's no need to look at the total change in diameter in the radial direction. In the radial direction, this delta R, the R refers to radial direction. So, thank you. Yes. And I will close the bracket. So total means that this is the total change. That means I have to use 16 into 10 power minus 3. Thanks for pointing out, by the way. So Poisson comes out to be, you can give me the value. Yeah. So it will be 0.25 and life is good. Hang on for a second. Let me look at the numbers. Yeah, this question did take more time than I anticipated. So you can just tell me the values. So epsilon x in your notes is? Okay, unitless. And you have epsilon r as?
1.5, negative 1.5.
Okay, and so here I will have epsilon x, which epsilon y or epsilon r, which is negative 1.5 into 10 power minus 4 divided by 6 into 10 power negative 4.25. Okay. After a few hiccups, we are back on track. Clear, right? Now, at this stage of the course, we don't talk about that, but I will write few formulas and we will just forget for a few weeks or probably for the full semester actually. But I really want to write some formulas just to give you a little perspective. and then we will solve one or two more problems. So is this clear? Should I proceed? Okay, everyone. Okay, so we have a few comments that I want to make. These are very important. Hooke's law. Do you remember Hooke's law? Anyone?
Yes.
What was that?
That equals 3 times.
Oh yeah. Yes, you're right. And I mean, yes, you're right. And then we also talked about stress is equal to elastic modulus is equal to stress over strain, right? Good. Life is really good right now. I'm about to add one more comment here, that epsilon x, is equal to stress x over E. But this happens in a uniaxial loading. If this happens in a uniaxial loading, so if I have an object like this, and I'm putting a load like this, and this is my, let's say, Fx or Px, whatever you want to call it. This is my reaction Px. I am in the elastic region. I ask you, give me the strain. You're like, so easy. But just imagine, what if I put another load here? Are you getting my point? Now, this is not straightforward. Because, so just your internet connection is unstable. Okay. So just imagine if I am also trying to, if I am pulling it like this, and I'm also pulling it like this, life is not that easy anymore. And just imagine if I also pull from here. So now I have Py here, XY, let's say, yeah, and Py here, let's say, and my PZ is acting like this. Whatever. So I will have to use something else, and I will write the formula, and we will not use it. Probably not in this semester. Probably in your 434, your next instructor will use 1 over E stress X minus fill in the blanks and stress Y plus stress Z. This fill in the blank you will tell me. And then epsilon Y equal to 1 over E stress Y minus fill in the blank. All of you will decide today and will tell me. That's such a nice answer. You are 100% correct. Fantastic. Poisson's ratio. And this is stress X plus fill in the blank. Stress Z, bracket close, and epsilon Z equal to 1 over E. Again, we will not use these formulas. 434, your next instructor will teach you this. Where is this? Stress Z minus. We can talk about it, by the way, but this just goes well beyond the scope of the course. We have too many things to discuss. Is this clear or not? Yes, no?
Final equation, I couldn't get it to them. Why we did kind of equation, like 1.5.
Third one?
Yeah, EX, EY, and EZ. We said that 1.5 E times square bracket.
Oh, you mean I do? Oh, I mean you say you're not sure about this one?
No, I couldn't get that part.
Oh yeah. So for example, I can explain to you like this. How should I explain to you like this? Look. Okay. So for example, if I am pulling it like this, right? If I am only putting a load in the X direction, then I will have a, yes, I understood. Now I will explain. Look, if I have this object, right? If I ask you, I am putting a load like this, right? All of you will tell me that there will be a strain in the X direction. Done. Now just imagine I am also putting a load like this. How will the object behave? You will tell me that if you are putting a load like, exactly right, putting a load like this, then the object wants to elongate more. And if I put a load like this in the Z direction, in this direction, you will tell me that the object also wants to elongate because of that. Yeah, so that's the answer to your question, that essentially it's the Poisson ratio. You multiply it with those loadings, and at the end of the day, everything contributes to the epsilon x. Okay, again, that's just a little beyond the scope of your course. One more formula. So let me write MEC 434. If we ever decide to include this in our course, I will send you an email. MEC 434, MEC 434. Okay, one more formula. Okay, so this is G. This is shear stress. You will fill in the blank for me. Elastic modulus is equal to normal stress over normal strain. Modulus of rigidity equal to shear stress over shear strain. Okay, so this is known as Young's modulus, modulus of elasticity. It has dozens of names. I'm exaggerating, probably 2, 3. Modulus of elasticity, whatever. This is known as modulus of rigidity. Cram it, memorize it. Modulus of rigidity. Okay, this is definitely 206. I will probably use it. You will use it. Done? Okay. So far, so good. I'm just adding piece by piece. Okay.
Can we calculate this by using matrices?
Yes, absolutely right. Which one? The strains, right? 100%. So if you Google right now, Hooke's law, stress strain, enter Wikipedia page, click on that, scroll down. There is a big matrix written between strain and stresses on Wikipedia page. But again, right now, I don't find any reason why should we start doing that. But the answer to your question is 100% yes. Okay, why don't you all tell me the formula for Poisson's ratio without looking at your notes? What was the formula for Poisson's ratio? Okay, transverse, transverse. Okay, so everyone remembers that. That means, well, since you remember, which is nice, epsilon y by epsilon x. Okay, G equal to modulus of rigidity is connected to the elastic modulus by this formula, E over 2 into 1 plus mu. If I were you, I will just memorize it. I already memorized it, by the way, more than a decade back. Memorize it. Okay, so now we have 3 important properties. 1, elastic modulus. 2, Poisson's ratio. 3, modulus of rigidity. Let's do a nice and beautiful problem. And this problem, you are doing it. 100%. I'm not doing it. So let us have, oh, come on, where is the problem? Yeah, here is it. So let me formulate the problem for you. The problem says that I have this nice and beautiful test specimen. So we are standing in a lab setting, okay? But you have to understand, okay, I think I need to clarify a few things. This Poisson ratio, for example, is given by the manufacturer. Okay, the Poisson ratio is definitely given by the manufacturer. So right now, let's say we have this experiment that we are conducting ourselves in a lab setting. I have a specimen. And I am conducting this experiment to find the properties of the material. I put a load of 100 Newton in the lab, axial loading. Nice and beautiful. This is axial loading, please. It's just bad drawing. $100. Okay. And I have marked two nice points here. One point is marked here by me, one point is marked here by me. And the distance between the points that I have marked in the lab is 300 millimeter. The diameter of this fellow is 50 millimeter. I hope I am not making a mistake in the dimensions. I think I'm right. Anyways, 50. Probably I will change them, but right now it seems correct. Now, it is observed that our delta A, so let me call, this is my A, okay, delta A is 0.219 millimeter. 0.219 millimeter, I mean in the axial direction. And I'm sorry, I think X, I mean, the X is in this direction, so axial. And then delta in the radial direction. Please don't call it as delta in radius, call it as radial direction. That is the change in the dia. That is hang on for a second. That is give me 1 second. 0.0219 millimeter. And that is also millimeter, please. Sorry. I am asking you, use the imagination and give me, find the elastic modulus, find Poisson's ratio, find the modulus of rigidity using this very simple lab test. So I made a mistake, by the way, it's millimeter. Okay. Let me double check the values again. 300 millimeter. Yeah, okay. Make one more change, please. Make this as, you have to bear with me because it's hardly visible. 0.012 and make this 9 as a 5. No more changes. Even if it's wrong, we will go with it. Done. $100 kilonewtons. Okay. Okay, that's too many mistakes for one class, but anyways, that's 100 kilonewtons. Otherwise, you will get funny results. This is a solid shaft. Should I help you a little bit, everyone? Or you have already started? So elastic modulus is equal to stress over strain. I will find stress, force per unit area. Then I already know the strain, which is change in length 0.219 millimeter divided by 300 millimeter. Yes. Already done it. I have a little different answer for elastic modulus. I want to see your. Okay, do you have calculators? I think I have 70 in my notes, no? But my answer can be wrong, by the way. Okay, we will do it together. What about our online students? Did anyone do it? Ahsan, Sadek, Aisha. $300mm. By the way, did you observe that the total length of the rod does not matter? You just mark the 2 points. Do you observe that, right? Because I am just caring about the 2 points. They are 300mm apart, and the change in length is 0.219mm. I never gave you the total dimension. So observe these very little details. Okay, everyone, I think I'm doing it because you never know if the values I have are wrong. So we know that elastic modulus is equal to stress over strain. Yeah, 70 gigapascals is in my notes. So it seems correct. Yeah, anyone else got 70? No, 70 gigapascals. I can even look at your notes. I can figure it out just by looking. It should be giga. I will tell you why. Because when you find the area, there will be an extra.
Oh, yes.
Right? Got it. Good, good. Everyone is with me. So E is equal to stress over strain. Stress is equal to force per unit area. Strain is change in length by original length. This is PL over EA. Okay, PL nod, if anyone wants to call it, I don't know. Okay, and excuse me. And then this will give me E equal to PL nod over delta A. Elastic modulus becomes, let me use a different color, 100 into 10 power 3. I'm so happy that I changed the values 3 times, but we have arrived at the right answers. L naught is 300 into 10 power minus 3 meter divided by delta. What was that? 0.219 into 10 power minus 3 meter multiplied by area. Okay, this is definitely I'm not doing it. What is the area for this 50mm chunk? Pi d square by 4. Anyone did that? Finding area is a, yeah, 1.96. 1.96. 1.96 pi d square by 4. Why don't you write it in your notes? Into 10 power minus 7. Correct? Can anyone just calculate the area for me, please? Pi d square by 4 for a 50mm solid. Minus 7. 10 power minus 7, right? Okay, meter square. Why don't you now give me elastic modulus? 70 gigapascals, right? So let me use the same color. Okay, everyone. Okay, let me first ask you. So did you figure out where was the mistake?
Almost the lower parts.
Here?
Which is, right, and did it come from?
This one?
Yes.
This is area. So diameter is 50.
Yeah.
So I do
But that's value.
a pi d square by 4. Pi multiplied by 50 square over 4.
So the area of the diameter is different, right?
Yes, it's dia that is given to me and I had to find the circular area. So that would be quite scary. Okay, everyone. Life can't be better for us. Done? Time is also done on 12:13. What about the rest of the quantities? Poisson's ratio will be 0.33. So it will be epsilon x. I'm sorry, not epsilon x. I think epsilon y over epsilon x, which will be equal to so transverse is 0.01215. Okay, I might be wrong here. Let's see, 0.01215 into 10 power minus 3 meter transverse divided by the diameter, which is 50 millimeter. Then this chunk will be divided by epsilon x, which is the change in length in the x direction. Oh, come on, what was that? What was epsilon x? Delta x, 0.219. 0.219 into 10 power minus 3 meter divided by the original length is 300. That is one calculation that everyone has to do, by the way. Let's see what answer we are getting. We really want someone to please don't make a mistake and tell us the answer very carefully. Huh? What? Oh, epsilon x is in the axial direction. So even in this class, whenever I take the x-axis, you will observe that I keep on taking the x-axis along the axis of the object. So I need to be clear here that this is my epsilon x. Huh? Okay. Someone tell me you got 0.33. You did? Really? Everyone?
What was done? Previous question, we used the radius. In this one, we used the diameter. While we are finding.
No. I in the last question, I also clarified. Okay, I will have to go back. Okay, everyone, give me 1 second. You remember where was that? I clarified that don't call this as change in radius. This is the total change in the diameter in the radial direction. You see, total change in diameter, the R stands for radial direction. So please keep this in mind that this is not change in radius. This is the total change in the radial direction, exactly like this is the total change in the x direction. This is the total, and when total automatically means the diameter, huh? Okay, why don't you give me the modulus of rigidity? And yes, sir.
Can we write ER epsilon R instead of ER?
Oh yeah, absolutely. You are 100% right. In fact, I will do it. His question is, can we write epsilon R? Oh yeah. In fact, why did I even write epsilon Y? Why didn't I write epsilon Z, for example? So the best method is write epsilon R here. I agree with you. Okay, very good, very good. Epsilon, I will make a comment here, or epsilon Z, or better option, I agree with you actually, that write epsilon radial. Give me the value of G, by the way. I think you are right. I think all of you are right. 26 gigapascal. And why don't you tell me, so shear stress over fill in the blank equal to shear strength. But this is something that all of you need to remember it.
Yeah.
Yes.
What we find for the Poisson ratio?
What is what?
Poisson.
Poisson's ratio is 0.33.
0.3. Okay.
Yeah, Poisson's ratio. I think I need to stop using this green color. It's not that visible, no? But anyways, next time I will not use it. Okay, everyone. We still have 12 minutes, by the way. I think I need to give you you can say a take-home question then, because we will not be able to finish that here. let me give you a take-home question. Use your imagination and do it. Okay, that question will be from strain, by the way. Uh, let me think about it. Please give me 1 minute. So far, so good, right? Yes, I think I need to make an announcement. Okay, so homework policy, I have to clarify one thing. I have mentioned this, I will reiterate. So yes, it's true that homework will be graded generously, but we have actually a teaching assistant with us. He just joined us. His name is Khan. Yes, that's the right pronunciation. So what we have decided is that if you make a huge mistake in one of the problems, big mistake, like super big, conceptual, in graded homework submission. So for a 20-point problem, 5 points will be deducted because it's just a homework, it's for your own benefit. If there are minor mistakes, points will not be deducted. If you do not attempt a problem, of course, there will be a 0. Second thing is you are all allowed to ask me questions regarding graded homework. The only reason is that the solutions are already available online. So I think you all know this. The whole point of graded homework is for you to learn. Yeah, that's our class policy. If you want to comment on that, please tell me right now. Just bear with me for 1 more minute. I just want to make a problem. You do it yourself. Okay, yes, this is your take-home problem. Use your imagination. I highly doubt we will be able to complete that in this class. So I have a problem that goes around like this. We have, let's say a metallic wire or whatever. Then we have this, again, beam I'm considering as rigid, which is very funny because beams are not going to behave like a rigid body, but this is 3rd week of our course. Then we have a pin joint here. And the question says that I am hanging a nice and beautiful load from point B. We have done quite a few problems like these, by the way, now. Anyways, so the load is like this, nice and beautiful. Done. Let me call it as my mass M. The question says that if this is your point D, this is B, and this is my point A, and this is my point E, and this fellow is, oh, come on, the dimensions are so 8. Okay, you tell me the symbol. No.
8 foot.
8 feet, yeah. This one is 2 feet. This one is 3 feet. If I had used two bars, then 2 primes, then that would be inches. That is your in feet. The question says that if your delta ED, I have to stop using this color, by the way. Let us use this one. Delta ED is equal to 0.0417 inches. Why don't you tell me find and delta find W equal to mg equal to question mark. And you also have to find or determine. I think determine is the right English. Also determine how much the mass drops, how much it goes down. Okay, why don't you ask me if I have missed anything? Double check. Did I give you everything?
Should all the digits?
Oh, of course. This is not a real life beam. It's rigid. Beam is rigid, behaving like a rigid body. A very ridiculous assumption. So let me make at least a small diagram for all of you. So all of us are on the same page. Let me use a very light yellow color. So this will become like this. Okay, so did I give you delta ED? Oh, yes, I did. So this I gave you as delta ED given. You have to give me this. So this is 2 feet. This is 3 feet. This is 4 feet. This is 8 feet. Okay, one more thing that I did not give you, I have to give you areas. Nobody reminded me this. You cannot do anything. The areas of these metallic wire, the green one, the black one, these are A36 steel. A36 steel. Why don't you Google A36 steel in your free time? The area is 0.0020 inch square. This is, yes, please, cables. DE and BC that I'm talking about. DE and BC. Elastic modulus. Sorry, I will take your question. Yes, please. Elastic modulus. Let me write down. You will not be able to do anything if I don't give you this. 29 into 10 power 3. Give me the units. Give me the units. Kilo, pound. No, it's in British unit. No? Kilo, pound per square inch. Yes, please.
Or mass drops means like.
Mass drop means, I will tell you, mass drop means that because of the fact that you have this cable that is stretching, this beam will drop, right? So this whole mass will also come down, right? But it doesn't stop there. This mass is also hanging with the cable, right? So because of that, you will have a change in length equal to force because of this PL over EA. So that change in length, intrinsically that is happening because of this load, you will have to add by this drop that happens because of this. Now, in order to do this problem, first I will encourage that you first use the similarity of triangles, get hold of this. Once you get hold of this, that is one dimension. Then in order to get this weight, you cannot do anything until you use the free body diagram. This arrow will be directed upward. This arrow will be directed downward. This where arrow will be acting upward. You will take the summation of moment, let's say about this. You have already, you know, the change in length of this wire that is equal to PL over EA. You will get hold of the load in this. If you get hold of the load of this fellow, you will do a summation of forces in the y direction and a summation of moments here to somehow get hold of load here. So I think now you will do it. So this is your take home problem. Sorry. C what? C is what? Yeah, sorry. Yes, this is point C. Thank you. Thank you for this is your point C. So major mistake, major mistake, negative 25%, completely leave the problem. That's 0 points. And yeah, yes. Any questions? Thank you. Have a nice day. For office hours, you know my email.
Upcoming lecture,
Okay, Sadek. Okay, Aisha. Bye bye. Yes.
for the upcoming lectures, do we solve this problem or we're just giving the answer for you?
Solve the problem, and when you arrive in class, you can ask me questions if you have. But this is not a graded task for you. It's for your own. Use your imagination. Use your skills. Yes.
Can I ask something?
100%.